Dear friends, welcome to my video. Kindly click on the CC button for subtitles. Among the many revolutionary concepts introduced by quantum mechanics, the Heisenberg Uncertainty Principle stands out. This principle changed our understanding of the fundamental nature of particles and, consequently, our perception of reality. Formulated by German physicist Werner Heisenberg in 1927, the uncertainty principle provides a foundational principle for quantum theory. This principle doesn't stem from the limitations of our measuring devices, rather it is woven into the very fabric of the universe. In its simplest form, the uncertainty principle states that it is impossible to simultaneously measure both the position, x, and momentum, p, of a particle with absolute precision. The more accurately we determine one quantity, the less accurately we can know the other. This is symbolically represented as increment x increment p is greater than or equal to h2, where increment x is the uncertainty in position, increment p is the uncertainty in momentum, and h is Planck's constant divided by 2 pi. At first glance, this might seem counterintuitive. After all, in our daily experiences, we can know both the speed and the location of an object, such as a car, quite precisely. However, at the quantum scale, things work very differently. Contrary to classical mechanics where particles are considered as distinct entities with well-defined trajectories, quantum particles behave both as particles and waves, a concept known as wave-particle duality. When a quantum particle is observed as a wave, it is spread out in space, making its position uncertain. This wave-like property introduces the concept of quantum superposition, the idea that particles can exist in multiple states simultaneously until observed. Let's take an electron circling a nucleus in an atom. In the quantum world, the electron doesn't have a specific path or position until measured. Instead, it exists in a cloud around the nucleus, where the density of the cloud represents the probability of finding the electron in a certain location. This is in stark contrast to the solar system-like model of the atom from classical physics. The quantum, cloud, or wave function illustrates the reality of the uncertainty principle. The very act of observing or measuring disturbs the system. The more precisely you measure the electron's position, collapsing the cloud into a more specific location, the more you disturb its momentum. Consequently, the wave function shifts, rendering the exact momentum of the electron uncertain. The converse is also true. If you precisely measure the momentum, the position becomes less certain. This doesn't mean that quantum particles are chaotic or unbound by rules. Instead, they adhere to statistical laws that define their behavior within the confines of uncertainty. The quantum world is not a world of chaos, but one of quantum randomness, with probabilities at its core. Moreover, the uncertainty principle has profound implications on the idea of determinism, which underpins classical physics. While Newton's laws of motion can predict the future state of a classical system given its current state, the uncertainty principle suggests that such predictability is fundamentally impossible in the quantum realm. In conclusion, the Heisenberg Uncertainty Principle is an essential and truly revolutionary concept in quantum mechanics. It asserts an inherent uncertainty in the simultaneous measurements of certain pairs of physical quantities. Far from being a mere technical complication, it forces us to revise our views on the fundamental nature of reality. The world at its most basic quantum level is not deterministic and definite, but probabilistic and somewhat blurry. Understanding this principle brings us one step closer to understanding the beautiful and bizarre world of quantum mechanics. Thank you for watching my video. Kindly subscribe to my YouTube channel and give a thumbs up. Thanks for your support.